Swayam Prabha. Digital India. Educated India.
Welcome friends once again to our NPTEL MOOC module on health economics. We have been explaining the chapter on health efficiency or the week on health efficiency. The specific chapter is in continuation to the DEA model, that is data environment analysis. The specific goals of this particular lecture, which is in continuation to the previous one, we are actually going to clarify further on the output oriented CCR model, that is the CRS model, and we are also emphasizing once again on the BCC model. We discussed just the basics, but now we are clarifying the BCC model, its respective derivation and its particular efficiency scores, etc. Will also clarify the conditions on efficiency scores and the efficient targets. So, to start with, this is the one we have said already. There are three important approaches. Basically, in the previous lecture we discussed about the formulation and estimation that is based on three forms of input oriented CCR model. This is largely explained. Here we will be emphasizing on the output oriented CCR model. As to explain in short, starting with the ratio form, then we will discuss a bit of multiplier form, and then we will discuss about DF, envelopment form. So, in the input oriented model of the CCR input model, especially that is based on the principles of constant tends to scale. The objective function is to maximize, subject to maximize the output with respect to the inputs and their respective respective weights. We already emphasized in our earlier lectures, and this is indeed our objective function. And in the input oriented model, we take it as theta, and subject to the constant is here where we say that the other DMUs and their output to inputs should be actually less than equal to 1. Then only we can able to discuss about the maximization of the concerned DMUs and their respective output. Okay. So, and the weights which were just discussed should be actually positive. Okay. And for all rth level of output and ith level of inputs. Okay. So, now maximizing the efficiency rating theta for DMUs O is our the Oth DMOs we are discussing. So, and we have already discussed about our constant function as well, and the constant function where the U and V coefficients are also taken and their respective weights are also multiplied with the output and inputs respectively. No DMUs will be more than efficiency score 1. That is what we have already explained. Now, though we have talked about this in the previous lecture, but the expanded form was not discussed. Here is the expanded form, how it looks like exactly. So, actually since we said summation of U R and Y R O for the Rth, for the Oth DMUs and Rth output of its, you can just see how the width input width output is actually or the width not output width DMU is actually mentioned everywhere. Okay. And for their respective weights and their outputs are also discussed. Here is the outputs, here is the output. Okay. Similarly, it is actually, since we are emphasizing on the ratio form, so we are taking as a ratio to their respective inputs. Okay. And inputs and their respective weights are multiplied. So, as a summation, since summation we have already considered in our formula and as per the original suggestions. So, these are all. Now, you can further clarify your concepts like for the DMU1, DMU2, similarly till DMUj as far as the constant function is concerned. Each DMUs and they are not in the objective function, that should be less than equal to 1. You can just have a look. Now, this is for the first DMU, you can everywhere it is 1. Okay. And for rth level of output, everywhere we are actually concerning with the rth level of output. So, this is till the r you can just see this is written as rth. Okay, for the respective DMU, that is at this moment we are explaining 1, and it has to be ensured that the summation should be less than 1 as a ratio. Okay. Similarly, for DMU2 and till DMUj. Okay. And this is how it looks like, and it is actually calculated in a disaggregated format. And we are sticking to the input oriented model, and in short it is also called CCR-IN. So, in terms of and now in terms of output oriented model, that is called CCR-out, and in that case the approach is to minimize the cost with respect to output, and that's we usually take in that case we take another symbol. We will just discuss, but in the input oriented model we have taken as theta. Okay. And here the minimization of input with respect to the output subject to its constants for the jth DMUs, and I will also clarify what is this Vi and or UR and VR. That is precisely the weights, but the exact clarification is called they are their limit should be very at a very smaller number, and that is actually called Archimedean element. Okay, noted by E, epsilon E. It is actually noted as very small element, and that should be higher than 0, and that U and V should be not very high, it should be very less, and it should be positive real number. Okay. And these are all we have also partly discussed earlier, but further clarification was just given. Now, in terms of another form called multiplier form, how input oriented model looks like, and we explained earlier that it is multiplied with the respective weight to its output of the concerned DMU, that is with DMO, and our objective function is mentioned as theta. Okay. Subject to the difference between the output of the jth DMUs to the jth inputs. Okay, jth DMUs and their respective inputs, and the summation is also made, and the constant function is clearly clarifying that the difference should be also less than equal to 0, and it is attached with another constant function, and especially on the inputs of the Oth, that is the DMUs unit and its input should be the sum of the inputs should be 1, and we have already clarified that the UR and VI should be positive. Actually, this is this multiplier method and in the CCR form or the input oriented method can be also written as maximize Z with respect to mu. Mu is also written and rest are more or less same, and mu is actually also interpreted. The transformation developed by this transformation is developed by Chance and Cooper in 1962 for linear fractional programming. Selects a representative solution, and that is the solution is U and V, for which the product of it Vi Xi for the inputs okay, so of the Oth DMU should be equal to 1. This yields the equivalent linear programming problem in which the change of variables from U and V to mu and V is a result, and mentioned by Chance Cooper transformation. Okay, that's why it is called a transformation. And in output oriented format, that is called CCR output. This is just the reverse, and it is simply mentioned as minimum of Q. G we take in maximization of output subject to its constants, but here it is just the reverse as minimization of inputs of the Oth DMOs. So, again if you are following very correctly, this is the DMU concerned DMU unit, and even the Archimedes E is also written, and its value we have defined already in the previous slide, and now mu is actually a transform format. The solution remains same in ratio and even in multiplier form. That is another note you can also follow. Now, the most awaited one with our title of the chapter, the lecture is on envelopment form, and its expanded format will explain, and its the full form will also explain. The theta, as I already mentioned, this is input oriented one, whereas the in the output one we use phi. Okay, theta star, that is to minimize the theta subject to the constants. Here the constants are already explained in the earlier lecture, but the respective potential efficiency score which we derive from the envelopment form has to be a product of its first constraint, okay, in the inputs. Okay, and then the lambda coefficients associated with the quantity of output and input utilize its production. Another one is on output aspects. So, we can just check the difference very clearly. This is where we say maximization of output, that is the symbol is taken as phi subject to, again in this case the constant function is deriving the potential efficiency score of phi, and that is part of the constant function, and lambda at its respective coefficient associated with the quantity of input, output, etc. is also considered. And the full model is written like this, where we are also encapsulating or understanding the slacks. The slacks we have already, input slack and output slacks we have already discussed. In the full model, we are not just only directing the minimization of minimization of inputs to output, or maximization of output to input, etc. So, here the slacks are actually respectively mentioned, and subject to the, even in the subject constant function we have included its respective slacks. Okay, and its coverage is mentioned. Similarly, in the output oriented model, the slacks are also discussed. You can just see how it's, of course, the slacks in the input case we are trying to minimize the input, where in the therefore it is minus, where in the output oriented model the slacks are actually additionally improving your extent of output, and rest are also taken care of in the slacks are also taken care of in the constant function as well. We are referring to the work of Afriet 1972, Fair, Groskopf, Logan, Banker, etc. They suggested adjusting the CRS DA model. Okay. Hence, this is presented here. When economy of scale exists, then what really happens? What do you mean by this? Basically, this suggests if a proportional increase in one or more inputs can cause greater than proportional change or increase in outputs. Similarly, a proportional increase in inputs may yield a less than proportional increase in output. So, in the CRS input oriented DA framework, we have taken 5 forms, as I already said. 2 are inputs and a single output. So, output is here Q, and the DMU is 5. Here are DMUs. We will stick to a specific DMU and we will also clarify how it works in software. In our next lecture, we will give you the direct application, how you guys can able to also derive results and what should be the interpretation. So, here for a radial measure, we are taking with respect to their respective output of the inputs. Hence, those can be measured x1 upon q and x2 upon q, and so input output ratio for this example are plotted in this picture or in this graph. This DA frontier which is derived and highlighted in bold line and written as frontier in our graph is indeed the result of running 5 linear programming problems. So, there are 5 linear programming problems. We will just clarify. For form 3, we are now sticking to this form 3, okay, and how the efficiency are calculated from the distance we already explained, and here the form 3 particularly the target is minimize q with respect to the constants, okay, that is for the other one other subject to the constant is that here it is minus q3 plus q1 lambda 1 and q2 lambda 2, then q3 lambda 3 and so on, that has to be greater than is equal to 0, because that is the constant function we already discussed. And for and then other constant since other 2 constant function are also mentioned, q3 I mean sorry the theta times x1 3, okay, and then the constant has to be subtracted from the theta x1 3, then theta x2 3 for all lambda to be positive. So, now you can just have a look the values of theta and lambda which provide a minimum value for theta are actually discussed here. So, in the figure we have tried to give the directions for IS. Here IS stands for the input slacks and OS stands for the output slacks for all 5 DMUs, okay. So, you can just see for especially for form 3 which you have already started explaining. Form 3 the figure is here, the theta value is actually the is 0.833, we are just presenting here. Form 3 could possibly reduce the consumption of all inputs by 1 minus this theta, that is around 16.7% without reducing its output, all right. And this implies production at the point denoted at 3 prime. You can just have a check, 3 prime is here, alright. And this projected point 3 prime lies on a line joining point 2 and point 5, okay, this straight line, alright. And therefore, form 2 and 5 are usually referred to as the peers of form 3, okay. And they define where the relevant part of the frontier is, and hence they define efficient production for the form 3. For the point 3 prime is basically a linear combination of point 2 and 5, where the weights in this linear combination are with the lambdas which we already discussed, okay, lambdas in row 3 of the above table which we already discussed, this lambda, okay, this row 3 and their respective lambdas, okay. In this case we are actually discussing this and this, okay. And then these are I think the clarification related to the CCR model, which is very basic so far as efficiency scores based on CCR is concerned, and that is based on the constant returns to scale assumption. Hence, that is not capturing the specific efficiency. Indeed, the constant returns to scale captures the general efficiency score or total efficiency score. That is really divided into either pure efficiency score or pure efficiency and scale efficiency. Sometimes pure efficiency is also called managerial efficiency, and we will also clarify. And when we say pure efficiency, we are actually referring to the production function, which is in reality pure or in reality following variable returns to scale. Hence, the returns to scale models are referred in the context of BCC. Okay, BCC we already clarified in your previous 2 lectures. The CRS constant return scale assumption is appropriate when all firms are operating at an optimal scale. Okay. Due to imperfect competition, government regulations and constraints on finance etc., firm to be not operating at optimal scale. Okay. So, again referring these papers for further details. CRS we suggested adjusting the CRS DA model, I think we referred already, and we also discussed this part in the previous slide. The CRS linear programming problem is easily extended to account by the VRS variable returns to scale by adding to the convexity constant to CCR. So, given the CCR as a constant linear function, production function, we are actually addressing convexity constant to as comparison to the CCR. So, we will clarify. Convexity constant basically it forms a convex hull or envelope data points more tightly to the CRS conical hull. The CRS, if you remember, it is the upward sloping from the origin and the 45-degree line defining one optimum efficiency score. From there we are going to define the production possibility or the production function, which is actually forming a convex hull or the points which are very tightly defining to the constant returns to scale, that is linear conical hull. This provides technical efficiency scores that are greater than or equal to those obtained using the CRS model. Convexity constants ensure that an inefficient firm is only benchmarked against the firms of a similar size. That is another important direction. This is here we are actually benchmarking, but in the earlier case we are not actually benchmarking to a similar size, that may be the sizes might be different in the CCR model. So, we are going to emphasize the convex combinations once again. In CCR they did not actually scale up and scale down included in PPS and overutilizing or underutilizing one, and in CCR overall technical efficiency as I already mentioned, and inefficiency occurs due to 2 reasons, and indirectly actually we are estimating the inefficiency to identify the efficiencies. So, we are actually emphasizing at this moment on managerial efficiency or due to the scale inappropriate scale size use. Hence, BCC, that is the pure technical efficiency or the managerial efficiency, is defined like this. So, here we are actually referring to the BCC model. Okay. And in CRS DA, firm may be benchmarked against firms that are substantially larger than it. Okay. But in that case, in the BCC model, we are defining that should be equal to 1. That means in the CRS DA, the lambda sum should be less than or greater than 1. Okay. But in this case, lambda should be equal to 1 in BCC model. So, the BCC is actually called the pure technical efficiency model or efficiency managerial efficiency model or score. We are going to get the managerial efficiency score in this case. So, the overall technical efficiency score is nothing but the pure technical score times the scale efficiency, or scale efficiency can be derived with OT divided by PT. Okay. So, in the figure which I already mentioned that this is based on the CRS frontier, and this is based on the the production possibility which is nonlinear or different right now like this. It is actually called based on the variable returns to scale principle, and so this is also called VRS frontier, and you can see for DMUs P, if you refer here DMUs P. So, the input oriented model, that is the theta CCR for the OAth organizations which already discussed. It is here the OAth organization is we are actually referring to the P. Okay. That is the, so in this case the OAth DMU is mentioned. So, here the theta is calculated as AP, APC, APC you can just see divided by AP, okay, divided by AP, alright. Whereas in the BCC framework or principle, it is APV, APV divided by AP. For the BCC you can just see this divided by AP. Alright, since PS frontier, Pth level of frontier is mentioned as P, and the optimum frontier size is respectively different. This is 1 in CCR case and this is in BCC case. Okay. So, optimal scale size is defined at R, because in BCC as well as in CCR both are equal. If the theta in the CCR model is less than equal to the theta value in BCC model, in that case the overall technical efficiency is actually lesser than that of the the pure technical efficiency. Okay. So, in the BCC model which you already discussed, the full format of the BCC model we already discussed, including the slacks. Okay, and the target was to minimize the theta, and the constant functions are also respectively mentioned. And here you can see the sum of lambda which already said for the jth jth constant DMUs, that should be actually equal to 1. And that is also called convexity constant. To form the convexity constant, that has to be equal to 1. So, BCC that is the BCC is equal to CCR plus the convexity constants. Okay. And in the output oriented case, that is to maximize the phi minus all possible all possible slacks, and I think need to be corrected. It has to be, I will just go back and tell you. You can just see these are all discussed. I will come back to that line once again. So, this is what we already said. So, and you can just see This is what we have actually discussed. So, in the minimization case, lags has to be subtracted. In the maximization case, has to be added. Okay. So, thus just a minor correction will do it and explain it. So, this is what in the output oriented case. So, it has to be plus, isn't it? So, then rest of the details will be discussed. And another addition to the problem is that there are some efficient target we also discussed earlier lecture, input to output, and its respective targets are actually discussed with its respective slacks. Okay, and in the output oriented case also you can see the target is here and the phi is noted correctly. All right. Now, a firm may be benchmarked against firms that are substantially larger or smaller than it. For the lambda, some of their weights may be less than or greater than 1, which already discussed. But in this case, the jth firms and their sum of lambda should be equal to 1 to define the convexity constants. Let us be the case that there are 5 firms and single output using a single input. And considering input oriented DA, the data listed in this table, and yes, this is the case. So, single input and single output case, we are just trying to calculate the CRS based technical efficiency and VRS based technical efficiency score. In CRS based, simply it is, if suppose in 2th in second form, okay, second form it will be equal to, you can see 2, it will be actually output by input. So, 2 by 4, 1 by 2, 2 by 4, it is like this, 1 by 2 and 2 by 4, 3 by 3, etc. for CRS based estimation. Whereas in VRS based technical efficiency, you can see for the second form, I will just clarify, it will be actually 2.4 around this figure per second divided by the entire 4, this till this. Okay. So, this is what is the answer. And for the scale estimation, you can see it is basically the 0.5 divided by the CRS technical efficiency divided by VRS technical efficiency, which already we calculated, and hence it is 0.8. If it is actually 0.8, it signals increase in terms to scale, and this is how we are highlighting in the diagram and also mentioned. This is the one for the VRS case, isn't it? And that has to be the first one is actually as simple as that, 2 by 1 by 2. Okay. So, the scale efficiency we have already discussed, and I have also clarified how this works. For the VRS is very important, CRS you can easily calculate. Here it is this divided by the entire. Okay. Similarly, for third it will be this distance divided by this distance, same distance. Okay. And then you can respectively calculate the others. All right. So, there are different healthcare perspectives which are important in this context. In the healthcare sector, imperfect competition constraints on finance, regulatory constraints on entry, merger, etc., result in organizations operating system to be inefficient and operating in a inefficient scale. Hence, the choice of CRS or VRS is an important decision making process, and this relies on analyst understanding of the market constraints facing firms within a particular sector. If the CRS technology is inappropriately applied, then all hospitals are operating at a suboptimal scale, and then the estimates of the technical efficiency will be confounded by scale efficiency effects. We need to note here that one shortcoming of measuring scale efficiency is that the value does not indicate whether the firm is operating in an area of increasing or decreasing returns to scale. This can be determined by running an additional DA problem with non-increasing returns to scale, that is NIRS as well. So, this aspect we will also address in our next lecture. I think this NIRS etc. is also mentioned here in this diagram. You can just have a look. NIRS frontier we have given, we will try to also clarify. Okay, and rest of the details are in your slides. I hope you must have received a number of directions, and you must have been charged enough to collect your data for measuring efficiency scores, and can differentiate this CCR and BCC model. So, these are important suggestions. I think the next lecture will be directly from the practical side, and will be estimating through the package. We will use that package or the software called DEEP software. All right. So, thank you. See you in the next class.